Here we go. We're going to start up now. I'm going to talk about the concept of microcontrollers. This is our lecture number 2. Lab 2 is going to be simply turn on 2 LEDs. And, although it may not seem like a big deal, we're going to be learning how, with a microcontroller, to wiggle a couple of ports, or specifically a couple of bits in a port. But look at the organization up there that you have. Of course, you have your PC, and most of you have laptops, are going to use that. Through the PC, you're going to develop the software, and then the software that you develop is going to be put on what we call the target, or the microcontroller. And through a USB facility, the cable, and there's a chip on your board as well, you're going to download to another chip, which is the MSP430. So if you remember from, or if you have your MSP430 right now, you'll notice that one of the chips on the board itself, kind of like in the middle, a little bit towards the bottom, it just sits up really high. That is the actual controller or microcontroller that you're going to be using. The LEDs are all the way at the bottom. And the whole concept of that is that you're going to give it power or no power to be able to light it up. Now, let's go back through electricity basics. Well, hold it. Let's do this first. So, as shown up there, the port is a bunch of wires coming out of the microcontroller. And how many do we have up there? 8, all right? 8. Have we done anything yet in class to put 8 things together? Oh, we put 8 bits together, right? So what we're going to be looking at is organizing it into a single byte of 8 bits, 0, 1, 2, 3, 4, 5, 6, 7. Remember, in computer world, we start counting at 0. This is what we call the least significant bit, and this is the most significant bit. And then we did calculations with this. Now, we could work with this in decimal, we could work with this in binary, we could work with this in hex. It is by far easier to actually see and relate to this in hex. So as a recap, if we identify that we want to have this contain the value 0001, 0010, that's going to be equal to what hexadecimal value? Give you a hint. We kind of split it right there, right? And then we grouped them in 4s to make a hexadecimal digit. So what's the value of 0001? 1 in hex. 0010. 2. Remember, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the first is 2. But remember that table I showed you? The table that discussed binary to hex? Good one to remember, or at least be able to derive, because you're going to use it a lot. And you may see it on a quiz or exam. Hint, hint, hint. So we talked about this port. And in this port, this would be, we would call this port 1 or P1. And we're going to do a lot of stuff with this port, with this P1 port. We're going to do some stuff with P2 by the end of this 5 weeks that we're doing this over. So port 1 has these 8 bits, of which they're labeled bit 0, 1, 2, 3, 4, 5, 6, 7. Now with these 8 bits, they're going to be hooked up to other bits of hardware. So or other devices of hardware. So we could use them to connect to switches and LEDs. Switches will serve as inputs, LEDs as outputs. And so if we have something like this being a switch, being an LED, well, let's take a look at those two ways to connect. So what you should imagine is that this is the microcontroller, and this is a wire coming out of the microcontroller representing one of the bits of one of the ports. And let's say, for grins, this is port 1, bit 1. That's a designation we often give that. And if it's connected to a resistor followed by an LED, and that's tied to ground. So, remember electricity? If I give this port 0 volts, that's 0 volts. This is how many volts? 0 volts, all right. Is there a change in voltage potential? Okay, everybody should be saying no, all right. So is there any current flow? None. So that means that this LED will have no current through it to excite the device inside the LED, and so that will not light. So you give it 3.3 volts, which is pretty typical for our microcontroller. All right, we have 3.3. Do I have a value up there on that? No, I'm going to do it. 3.3, and let's say this is a 1,000 ohm resistor, so it'll go through. Oh, do we have a change in voltage? All right, so that means that there will be some current flow. The question is how much? By the way, how do you know how much? You remember that from physics in high school? Do you remember from physics here? Have you had it here yet? How about any other class? Oh, you actually did in 1201. Good. All right. So what do we have? Well, we really don't see much resistance on this, so we kind of ignore it. So it's just this. So that means what? 3.3 volts is equal to I times 1,000. So I is equal to 3.3 over 1,000. Which is equal to 0.0033, which we would call 3.3 milliamps. 3, right? Or would it be? No, just 3. So we have 3.3 milliamps, which is a good low amount of current to be flowing. And so that would cause this LED to light up. Hence, we say that up there. So if you give it 3.3 volts on, give it 0 volts off, keeping in mind, of course, that we're working in the digital world, right? So in the digital world, 0 is logic 0, right? 0 volts is logic 0, and then logic 1 is our 3.3 volts. Now, you could also wire it in that direction, the one at the bottom. So if it's 3.3 volts on both sides, no flow, but if the microcontroller says it's 0 volts, then there would be a current draw or a current sink. We're going to do all of our designs like the very top. And one thing I should add, too, is the one at the very top, you'll be able to turn on and off that LED by using these ports. And oh, look at this. If we put a 1 there, that might mean that I want to light that LED. Or if I put a 0 there, that means I might want to not light that LED. So let's take a look in a little bit more detail about how to implement that. And this is basically the concept of lab number 2. So if you want to make it light up, 3.3 volts, we did that calculation. And, so I did all this on the board and I had it on the slide. There you go. At least you could keep track of it. Let's take a look at a switch then. By the way, did I give this a port number? I did not give it a port number, but I did here. So let's say we have a switch. So let's look at the two differences. When you have the switch and you don't press the switch, look what you have. So in that situation, the switch is not going to be an LED-like device. It's just going to identify what is tied to 0 volts and what is not tied to 0 volts. So you have that situation up there. You have VCC, you have a resistor, and you have port 1.1. Is there any, by the way, assuming that port 1.1 is not actually, has nothing in it to consume or has no resistance inside, it'll just observe what's going on at that point in time. So from that, is there any current flow in that current situation? There's no current flow, but what's the voltage at the port 1.1 pin? It's whatever VCC is, right? Because even though there's a resistor there, there's no current. So the voltage VCC is also on the other side of the resistor. Now, as soon as you press the switch, you basically tie a circuit that goes from VCC through the resistor and into ground. So in this case, once you do this, you have the wire directly tied to ground, which directly goes to P1.0. And you have there a resistor that will allow current to flow from VCC down to 0 volts. This is something we commonly call a pull-up resistor. We're going to see this later in class several times. So P1.1 is going to see what voltage in the bottom drawing? 0 volts, right? Because the current would have bled off all the voltage through the resistor. And in fact, what is the current going to be? 3.3 milliamps, again, because you have 1,000 ohms. So the microcontroller will read 0. That's a logical 0. And that's how we're going to use a switch in that situation. So as I more or less have alluded, we are going to use this microcontroller port to control LEDs and to read switches. By the way, reading switches you're going to be doing in lab number 3. But I thought I'd cover it now since we're talking the concept of microcontroller ports. And so we're going to write some C code. And I think, I never did poll this group. How many of you have taken 2103 or are currently taking ECGR 2103? All right. So only a couple of you have not taken programming? Oh, I said have taken 2103 or are currently in 2103. So you should have raised your hand, right? Okay. And you two have got programming before? Yeah. Okay, so everybody's had C++? You? All right, so I don't need to teach you C because C is a subset of C++. C is a really easy subset of C++. You don't have to worry about all the other concepts that object-oriented languages give you. So let's take a look at that. All we're going to be doing is you're going to be reading port 1. And all you have to do is say, look at that, P1 meaning port 1, in. So that means you're going to read whatever is connected to port 1. And then you're going to stuff it in a variable. Remember, the single equal sign is an assignment. And of course, C, you need the semicolon at the end. So since a port, in our case, is 8 bits, the result of this could be data that holds 0000, 0000 through 1111, 1111. In other words, there's going to be how many different combinations? 2 to the 8th, which is 256, right? But, you know, you may not have a lot of switches connected to that, so you'll only have a few situations where you'll have 256 real combinations that you could read. So there you go. That's it. Y'all understand all of that now? We're done with the class. We don't have to meet again. All right? Oh, you want me to go into a little bit more detail? I got some people that are like, no. So let's take this one. Assignment number 2. As I mentioned, you are going to, by the way, go to Moodle for the specific instructions on what you have to do. But it's more or less download the software, which you've already done, and compile, then put it on your board. The general concept is you have a PC, which is actually writing down or is downloading to your board. Of course, you're going to write the code, compile the code, download the target, run the code on the target, see Moodle for the due date, and make sure you demo it to a PC. And I'll have a demo for this right after or at the end of class. So we'll actually show you how to use the tools. Have you used the tools yet? I mean, other than booting it up? Have you written any code yet? Yeah, all right. I'm going to have to borrow somebody's board because I didn't bring one down with me. So the main concept of assignment number 2 is that you're going to be wiggling the port with the 2 LEDs. So the 2 LEDs are LED 1 and LED 2. LED 1 is connected to port 1, bit 0, and LED 2 is connected to port 1, bit 6. So, as you can imagine, and this is kind of the picture of it, this is what the actual board would look like. You're going to have to say, oh. If you wanted to light both LEDs, you didn't see that yet, did you? What do you think, what C code do you think you would write? So take a second or two, turn to your neighbor, and for a trip to the prize closet, did I mention a prize closet? I think I did for the recitation, right? So for a trip to the prize closet, by the way, I have a t-shirt now in the prize. Ooh, I have no idea what size it is, but I'm pretty certain it's not extra large. So for a trip to the prize closet, turn to your neighbor, figure it out, what C code you're going to write, and we'll meet back in a couple seconds. All right, raise a hand. Who wants to solve this one? All right. Have you got a prize? You already got a prize. You can't get 2. Did you get a prize yet? No. Okay, I'll let you do it. What is it?
I would say 01000001 equals capital P 1 capital O U T semicolon.
Okay. Remember, we're doing C, so the assignment, whatever you're assigning to it, has to be on the left-hand side. So, all right, I'll give somebody else a chance. Who else? All right, go ahead.
Capital P 1 capital O capital U capital T equals 0 1 0 0 0 0 0 1 semicolon.
All right, that's wrong. Yes, sir.
It's not like 0x forward 1?
That is correct. Ding, 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 ding. All right, what is this? This is decimal. How could that be decimal? It looks like it's binary, right? Did you put anything in there to identify it's going to be binary? No. So it assumes it's going to be decimal. So that's one of the nuances of C. Remember, we did the 0x41 or the 0x to identify hex. Default is decimal, and then binary is, and then I'm getting my boards mixed up. I can't remember if it's 0B with everything else or if it's everything else followed by B. So if I were to guess, I'd say it's probably like that. But I'll have to check on that. Yes, sir?
So you just put in 65 and it also work?
Is that 65? Yes, that would also work. So the decimal value of 65. Now, would you remember what that is? No. So which one would be easier to understand? Probably that one, but in my world, hexadecimal is a lot easier because it's a smaller, more compact designation, and very often we're doing a lot more than just a byte. Usually it's a lot more like a total of 4 bytes together at one time, sometimes 8 if you're looking at larger numbers. So I would say, for the sake of this class, I'm going to be doing this almost all the time in hexadecimal. So good try. You still get a trip to the prize closet. You still get a trip to the prize closet. Oh, you answered it. And you still get a trip to the prize closet. Oh, that's right. You get a new car, and you get a new car, and you get a new car. I'm sorry, my name's not Oprah. All right, so what it is in hex, you started passing it around? Okay. So, port 1, which we mentioned can light up only, if we wanted to light up only LED 1, which is all the way on the right-hand side, we would have port 1 out is equal to hex 01. If we wanted to light up only LED number 2, you would then say P1 out is equal to hex 40, or hex 40. To light up both, we said, of course, you're going to do both at the same time, so hex 41. And if you wanted to light up neither, what do you think you would write? Hex 00. I mean, you literally have to say hex 00 to turn it off if you've turned it on previously. Because once you turn it on, it stays on until you turn it off. Question?
So why wouldn't it work if you were applying current to all the relays as well, since they're not connected?
Ah, good question. Why would you not just say FF, right? You turn on everything. Well, you can. But later on, we're going to be turning on 2 LEDs, but we'll have 2 switches also attached. And one of the LEDs is not LED number 1. So if you actually turned on LED number 1 and number 2 and number 3, then you would get points off because I only want you to turn on 2 and 3. And LED number 3 is going to be an externally wired LED. And that's to give you some experience with using a breadboard and hooking up another circuit. That's lab number 3. We won't worry about that for now. Now, one thing I didn't tell you about is for LED number, and this is where you might get away with this, for all the LEDs are output devices, right? And you specifically have to say, oh, I want to make this port and this pin on that port an output device. So in this case, we have 2 LEDs, right? We have LED 1 and LED number 2, which are connected to, as we've said before, let's see. We said that this is LED 1 and this is LED 2. And if we wanted to turn it on both at the same time, oops, then we would need to use that bit pattern, which is 41. So if we want to also declare that they're output pins, you have to use the DIR location. So in this case, P1 DIR is going to be set to 41, which will say, all right, and now we're connecting an LED to this and to this pin. And then later on, you also have to turn it on and turn it off by saying P1 out is equal to 41 to turn them both on, and P1 out is equal to 0 hex if you want to turn them both off. Everybody understand that? I've just given you all of the basic microcontroller instructions to do this assignment. Cool beans, huh? Sure. Now, the assignment, I said, it has to be a certain amount of time between each flash. Do you remember, did I say 2 seconds on this one or 1.5?
1.5.
1.5. So you could do the really, really classy way, and there's some libraries that will tell you exactly what 1.5 seconds is. Or you could do the really quick and dirty, cheesy way that I can do, and this might work for you or might not, I'm not sure. But in this case, you already know this for loop instruction, right? Everybody got that? You had it in previous C? Yes? If you don't know it, tell me now. All right. If you do a for instruction for I equals 0 to maybe 100,000, incrementing 1 each time, it's going to take a certain amount of time to go through that instruction, even if you have nothing inside. And so you can do that to kind of delay. Now keep in mind, do you know the difference between an integer and a long integer? Yes or no? Okay, an integer is shorter and a long is longer. It's kind of like using the name itself to define it, right? So regular integer uses 16 bits for the value. And a long integer uses 32 bits. So you can do the signed and unsigned, but I'm going to use it signed so it's easy. So if we use 16 bits to represent the value of a number, it's going to be equal to 2 to the 15th minus 2 to the 15th. Or you could represent numbers from minus 2 to the 15th to positive 2 to the 15th minus 1. That's the range of those numbers. And what's the range of these numbers? It's 2 to the 31st, negative 2 to the 31st, to positive 2 to the 31st minus 1. Why do you think it's minus 1? You got to represent 0 somehow, right? But it's a total of 2 to the 32nd bits, or 2 to the 32nd numbers that you could represent. By the way, anybody got a calculator doing this right now? What is this about? 65 billion? $1 billion. No. It turns out to be about 2 billion. A little bit over 2 billion. About 2 billion to about positive 2 billion. So about 4 billion different numbers, right? All right, we're back up above. So you'll need to change the value of that variable. Make sure that you make it a long integer, otherwise you're going to have some problems. Now, you put all these concepts together, you have assignment number 2. And how many think you could do it right now? All right, just one or two of you? Or maybe I could just give it to you, right? And you could figure it all out. Well, these notes are a little bit older because this is actually the first group I've had where everybody has had 2103. When I did this previous semester, maybe half had had C and C++. So now that everybody understands C and C++, we're going to make robots next semester. Woo! Oh, but not in 1202, sorry. Oh, that's your program. You all know how, I like that. Start with a main. We're going to define our long integer. There's going to be a line up there, watchdog timer control. It's a big concept that I don't even want to go into, but when you develop really, really, really complex embedded systems, you need to have what's called a watchdog timer. Remember, we have to set the direction of that these are outputs. Then we're going to have this line there that says while. And you already know what a while does, right? But notice I say while. What does that mean? That's one very, very important characteristic of embedded systems is that when you say while 1, it is going to operate forever. And if you think about that projector and that wireless node, the cameras, etc., you never want them to stop running, right? So you'll always have a while 1 line somewhere in your code, which means it will go forever. And then what are we doing up there? You're going to light the LED by doing a P1 out with some value. You'll delay for, it says 2 seconds, or it could be 1.5 seconds, whatever it is. Then you're going to do another P1 out, then you're going to do another delay, and you're going to start all over again. And the code will give you the return 0. Easy enough, right? You could probably even demonstrate this to Suzanne on Thursday. Or do you have Wednesday office hours? I can't remember. Nope, okay. Or you have them this afternoon, right? All right. She did ask that on Tuesday, or on Thursday, keep in mind she's not going to be available after 9 o'clock because she has a test on Thursday morning. So we're not going to make her get a bad grade in that test, are we? Okay, good. There you go. That's all the code that is required for assignment number 2. So without further ado, let's look at a demo of our tool. Code Composer Studio will pop up. Who makes Code Composer Studio? Texas Instruments. Woohoo! All right. You never know when something like that will show up on an exam. Project, and I've given you, here I'll start from scratch. When you first start a project, start a new project, which you're going to be doing, it will give you some options, and we've instructed you to go ahead and make sure that you choose the MSP 430 G2553. This is in the notes for lab number 3, so you should see that no problem. That is the specific microcontroller that you're going to be using. Now, you need to give it a project name. I recommend you include no spaces in the name. So I'll just call this Lab 2 Demo. You can call it Lab 2. You're also going to be identifying, wow, this doesn't give me much of a choice here, an empty project with main.c. So choose that. And then when you finish it, it will give you all the code that you need to get ready to start your lab. And I kind of, in the PowerPoint slides, have given you the example of that. Look at that. Remember I talked about the watchdog timer? There it is. And it gives you the first line for the main program with a return 0. So literally all you have to do is put the good bits in there, right? And that was in the PowerPoint slides. They'll give you a hint, and that's online. Any general questions that we have right now? No?
What was the last 4 digits to that code that you said MSP430?
2553. It's actually in the lab number 2 assignment. It's the specific variant of the TI MSP430 microcontroller. All right, you all ready? You think you can do lab number 3? 2. Lab number 2? All right, that's it. Thank you very much.